All right, okay, so today we are looking at probability density functions. So our learning intention for this first lesson is to gain the knowledge of what a probability density function is and some of its features. Okay, so we will be successful if we can successfully describe a probability density function, identify continuous random variables, and record that the sum of all probabilities must be equal to 1. So let's start. All right, so the probability density function, it can be shortened, so in some books you might see the word PDF. So a PDF, it's not in our glossary, but it's described as a function of a continuous random variable whose integral gives the probability of P large X is less than or equal to small x. Okay, and that's from our Maths in Focus textbook. Okay, now capital X is the random variable. So when we want a continuous random variable, we are looking at things that do not have a finite start and finish. So for example, the length or height of a person, the length of a leaf, things that are measured will always fall into the continuous random variable. Okay, here I've got following data was collected. It doesn't really matter. This is, let's say, age group, so it's from 0 to 9, or it could be the height of some sort. It doesn't really matter. But here's our frequencies. The total of our frequencies from memory is 50. 6 plus 8, 11, 15, 7, and 3. Yeah, it's 50. All right. We can then calculate our relative frequency, so 6 over 50. We're just going to do, we'll just leave it in terms of 50, that's fine. Okay. Because this isn't really the part I want to show you, but basically it helps. All right, so from our data, we can create a histogram. Okay, so if I wanted to find the probability of a continuous random variable is less than 30, all right, so notice that in my histogram, the group center is in the middle of the column, and it's because it's continuous, the columns together. So if I want less than 30, so that's going to be all these variables here, this one, this, the sum of these 3. So this would be obviously 6 over 50 plus 8 over 50 plus 11 over 50. 19 plus 6 is 25 over 50, so a half. Yep. Now, if I wanted the probability of the random variable being larger than 30, so I'm wanting larger than 30, so that would include this one, this one, and this, the sum of those ones. So maybe I'll do that in black. So reading off the column, I've got 15 over 50 plus, it's probably easier just only because I've got the data, but we could use the graph, and 3 over 50, so 25. Once again, this one works out to be a half as well. Okay, now if I wanted to find the probability between 20 and less than or equal to 20, greater than or equal to 20 but less than 40, so greater than 20, that includes this one, but less than 40, so it includes these two in the middle. Alright, so 15 plus 11. And that would be 26 over 50. Okay, and so therefore you can find the probability of these things. Now, we can get more accurate if we maybe reduce the group sizes. So rather than them being from 0 to 9, I can maybe go from 0 to 5, and I'll get more information. this helps, but it's not the most appropriate or useful tool to do so. There's a better way to do it. So we could create a function or a curve that marries into these histogram, okay? And that's what a probability density function is, right? Once we create the curve, we can then find out more information. So here I'm limited to what my group sizes are. But if I wanted to find something like, let's say, from the ages of 15 to 23, having that curve, I can find out more information. Okay, so with a continuous probability distribution, you can't calculate the probability of a single event. You can't calculate the event of age group 11, yeah? Because what would happen is that you'd have a group with really a width of 0, and 0 times whatever height that might be would be 0. So that doesn't really work, but you'd always be able to do it when you have a range. There will always be a range. Okay, so the area under probability density function will always add up to 1, so because all probabilities add up to 1, and so therefore what we say is the integral of from a to b of a function dx is going to be the sum of 1. Okay, and if you're looking at our formula sheet on page 2, we have this formula here. So the probability of a continuous random variable where we want that should really have x. Okay, it's all as fine as r, if that's r. All right. Yeah. Okay. Sure. Of some particular event is from a to that particular event of f of x. Okay. So let us do some examples. So here's an example. Which of the following functions describes the continuous probability distribution? So we have f of x is 0.2 in the domain of 1 to 6. So from x equals 1 all the way to the 6, we got 0.2. So what we want to do is we want to actually calculate the area under this point. All right. So 6 take away 1 gives us a width of 5. All right, and it has a height of 0.2 or 1/5. So the area is the length times the width, which will give us 1. And as this area is equal to 1, this function f of x equals 0.2 in the domain of 1 to 6 is a PDF, a probability density function. Yeah. All right. Here's the next one. I've got a function f of x equals x over 12 in the domain from 0 to 6. That's what it would look like. So we're going to try to figure out, is the area under here 0 to 6? Okay, so there's what we could do. We could possibly go from 0 to 6 of, and I'll write as 1/12 of x dx, and does that equal to 1? Let's calculate. So to integrate, we're going to have 1 over 12 divided by 2, yeah, by raising the power. So 1 over 12 divided by 2 is going to give us 1 over 24 x squared. And if we're going from 0 to 6, what is the area under this curve? So 6 squared is 36. So 36 over 24 minus 0, yeah, is 36 over 24. So this is not 1, which is not equal to 1. Therefore, f of x from x12 in the domain of 0 to 6 is not a PDF. Okay, and this is why we had to do integration before we could do this topic. Okay. Let's look at these examples. So below, are these following? Are the following graphs a density function? Density functions. All right. So here we go. So we want to find the area under the curve or under the function. So I've got 1 to 5. So this is going to be 5 take 1 is 4 units. I have a height of 1/5. So 4 times 1/5 is 4/5. That is not equal to 1. So this is not a density function, a PDF. Okay. This one, I've got a length of 8, so 8 units. It's not a rectangle, it's a triangle. So I've got a perpendicular height of 1/4. So the area is 1/2 the base times the height. The base was 8 units. The height was 1/4. So 1/2 of 8 is 4, lots of 1/4s, which does equal 1. So this is a density function. Okay. The next one, last example. Given the continuous probability distribution, so I have f of x is kx cubed between 0 and 5, and then 0 for all other x's. So past 0, sorry, before 0 and past 5, it's 0, but between here we get this function k on x cubed. We want to find the value of k. Okay, so that means if I integrate, right, between the values of 0 and 5 of this function, okay, I need to get a value of 1 to figure out what k is. If I integrate that, so it's going to be k over 4 x4, x to the power 4, from 0 to 5, and we want this to equal to 1. Okay, so if I plug in 5 x to the power 4, so what we get is we get 625k over 4 minus 0, because 0 to the power 4 0, has to equal 1. Alright, so 625k over 4 equals to 1. So multiplying both sides by 4, dividing by 625, we get 4 over 625. Yep, and so k has to be that value. Okay, so going over our success criteria, remember that a probability density function is the curve that we can figure out that demonstrates the probability of all events of a continuous random variable. Continuous random variables are things that do not have a discrete or set value. It can take on many values, such as the length or height of something, and the sum of all probabilities must be 1. So the area under that curve has to be 1. Okay, thank you very much. Good luck.